Sure. Thank you. Thanks, Caroline. And let me go to presentation mode. So do you see the whole slide, right?
Yeah,
Okay,
yeah.
okay, great. Thank you so much. And thanks the EMAC team to for inviting me, for having me here. So I'm in the next 10, 12 minutes, I'm going to talk about the importance of opacity, motivation, and the science or the challenges or the assumptions behind, as well as the our mitigation and our database that we are providing. So usually I start showing observation in one side and characterization, all the fun RT radiative transfer modeling on the other side, and I say to bridge these two together, we need opacity. So opacity data are important because it provides you with a template to understand if you have, I don't know, water, if you have methane, if you have nitrogen as a background gas, and etc. And so a little bit about opacity data. When we talk about opacity, we talk and refer the line list. We are talking about the line position. We're talking about the broadening coefficients, like the impact of the broadeners, background gas on the absorber itself. We're talking about the spectral intensity. For example, if you're thinking about like ultra hot Jupiters, very high temperature, that's a different challenge, and that comes with the partition function. And as a result, there are different line lists outside. For example, here on the right hand side, you see water opacity data from different line lists. Some of them are laboratory, some of them are theoretical. And when you zoom in, you see the line position, you see extra lines, and these all are important because as a result, what Brogy and Mike Line showed, for example, in 2019 in high-res stuff, cross-correlation technique, these differences in the line position would translate to different C to O ratio, to different characterization. And the ultimate goal of space exploration and from like the missions that NASA send is understanding, better understanding, accurate and full understanding of those atmospheres. So another example is TIO and VO. The question is that has comes up over the past years, is that do we have TIO VO in ultra hot Jupiters like WASP 33b? Some people saying yes, some people saying no. Even if when you look at the thermodynamic simulation, you would imagine that you could answer this question, but coming to the observation slash modeling, it is a challenge, and a part of this challenge comes from the differences between the line list, between the opacity data that people use. For example, here you see for titanium oxide, comparing two cases, and you see it's a big noticeable difference between 6 to 9 micron, and also around 4, around 3. And it's not only limited to TIO. For VO, it's the same story. And so over the past 3, I guess 4, 5 years, I have been working and talking all over to to basically make awareness about it is important to use opacity and don't refer to it as available opacity. Like we use available opacity for water. That's not the right term. There are different line lists that people are using. And so it's important, first of all, to report it correctly in your literature, in your publication, and also to do comparison. For example, we did one comparison between different line lists for like water, for TIO, for ultra hot Jupiter, and we found up to 300 ppm difference in transmission, and up to um, um, I guess 100 or 80 in thermal emission. And this is very important because with James Webb, the noise floor is up to 10, 15. So this is one issue with the line list. The other issue is with the broadening agent. Like most of the broadening data, like opacity available, they are uh, they are specialized, and they were calculated for hydrogen and helium dominant atmosphere. But when you look at the diversity tells you different story. It tells you that we have in addition to hydrogen, helium, like Jupiter-like atmosphere, we have um, high abundance of water. We have CO2, we have CO, we have methane, and nitrogen, oxygen, and basically we have a huge population, a high percentage of population of super Earth, sub-Neptune, and this is important it is crucial to use the right uh, opacity data with the accurate or the appropriate broadening coefficients. Otherwise, an example that I showed on 2019 is that what if we use water with hydrogen and helium for modeling um, um, steam atmospheres, like atmospheres with high percentage of water. And when you look at their opacity data, there is a big differences as you see here, which what you see is the blue, which is water with self-broadening compared to water with hydrogen and helium. And there is one order of magnitude difference in the in the value for the absorption cross section or opacity. And when you look at, for example, their emission, which is this is synthetic spectra, right? You see the thermal emission; it's up to 250 ppm difference for the range of 500 to 900 Kelvin for the atmosphere. And this is definitely detectable and can induce bias on the characterization and on the chemistry that you extract, the abundance that you extract from the observational spectra. Uh, in summary, I would say that this slide shows a really good summary about what the concern is, what I told you, explained to you. In one hand, if you look at the top left, you see the majority of the planets in cycle one. They are super Earth, sub-Neptunes, and these super Earth sub-Neptunes, you expect to see high percentage of CO, CO2, and other abundance other than hydrogen and helium. And this would matter as I showed you for modeling their atmosphere. So we need accurate line lists, we need broadening coefficients, and also about the resolution uh, as you go from HST resolution, which is R equal 5, 50, 30, up to James Webb resolution, and also CRIRES and other like a very high resolution. You need the line position, accurate line position for these models, for these molecules. So one work I did during past 3 years, and I published it in 2021. I provided a set of opacities for super Earths, for exoplanets on brown dwarfs, including super Earths and also ultra hot Jupiters, for a wide range of temperature, pressure, and for different absorbers. And you can see a detailed information there, like explanation, and not only explanation about what opacity we use, what line lists, but also comparing different opacity data from different line lists, like from different line lists, as I showed you for TIO and others, what you expect. And also I provided 2 pages, I think, just the challenges we have, because it's not reliable if someone, and this is fundamental work, this is like data, opacity data is something that most people are using, right, in modeling. Otherwise, you can't do modeling, RT modeling. So these are very important, and it's important to provide and to know what broadening and etc. are using. So one program that Natasha Battaglia, my colleague at NASA Ames, is leading is Maestro database, opacity database, which is, there are many people from, as you see, from Hytran and ExoMol group and others are involving in. And so the idea is to provide opacity data, which is validated and with all the information and etc. to the public. And you can go to this website. The link is here at nasa.gov. And then, for example, for TIO, and then you see there is information, there are different options for temperature, and also the details about the references, the information for broadening, and also you can zoom in on the data. So with that, um, I I would say, yeah, please feel free to contact us, either like reach out to Natasha or me, and also it's publicly available. You can use, and also if you have data, you can share. Again, reach out for more details. Thank you so much.
Thanks a lot, Ehsan, for a great talk. I see a question in the chat. Oh, okay, no, that was just a comment. All right, so I don't see a question on Slack yet. I have a small, maybe silly question. So some of these differences between different line lists, you can only see at high resolution. And so it's not as big of a problem for low resolution observations. But some, as you showed for like TIO, VO, I think it was the VO example, you can see like huge differences. And I wonder, to what extent can some of the discrepancies be solved by observations, kind of testing and seeing a molecule and then being like, oh, we should maybe trust this opacity source more than the other one. So it's probably not doable maybe not doable at high resolution, but for the lower resolution where you were showing kind of the big features that had huge differences, I wonder, like, how much of this can be solved observationally, or is it just a
Well,
lot
this
of...
is not an observational issue. Like to mitigate and solve this, this is laboratory. This is a spectroscopic work, and so I would say just to correct. I have a comment about your question. So these differences, some of them are important for high resolution, but also some of them are important in even low resolution, like in HST resolution, like the spectrum I showed, it's for like very low resolution. And so I would say it depends. There are multiple line lists, but what our group are doing and the team that I showed, there are people doing lab work, there are people doing ab initio work, there are people doing modeling work, and it's a combination of all people with different expertise to provide a single product, which is opacity data validated, and it's ready to use to be utilized for RT modeling.
Okay, awesome. Thanks a lot.